lightning talk, which is, and what we'd like to remind you of is to post your questions in the chat box. We'll address all the questions collectively at the end of the session, which will be at around about 11 and when we wrap up. So the next speaker we have in store for you is Mr. Braam Greeff. He's the Principal Systems Engineer at CSIR as well. And he headed up our project in the RTIMS program related to underground communications, a network at the stope, where he will expand on 5 use cases that were identified and how they would apply to the work that we are currently doing.
Good day, my name is Braam Greeff. I'm a Principal System Engineer at the CSIR, working specifically in the Defence, Security and Mining cluster area. And I'd like to address you today regarding the research work that we've done in developing a new underground network communication capability for possible use at stope mining work areas of the future. I'm going to give you a presentation that looks at the development approach that we followed, some of the evaluation work that we've done at the test mine, and then communicate some of the findings and the way forward that we decided upon at the end of our work. Now, just to give you some context about what stope face mining communication systems is all about, is that it's all about that last 100 meters from the infrastructure that you have to the stope, which is basically dark, no electricity, very rugged conditions. Typically, stope mining work areas are unpredictable. There's lots of non-line of sight conditions where you have to communicate. Lots of mobile activity, vehicles, mining vehicles moving around, a lot of dynamic things happening, miners moving around, material moving around. And in that context, you have to communicate, which is usually difficult for normal off-the-shelf communication equipment. Our development approach or research approach was basically focused on the following. We kicked off with a concept of operations where we looked at technologies, processes, and people and how they should work together to make stope face mining communication capabilities a reality. We developed some requirements. From that, we derived a demonstration architecture, which we eventually integrated and demonstrated at a mine near Rustenburg, a chrome mine, Kroondal mine, where we evaluated the technology in the stope area as well. Looking back to a previous research phase, we did do some initial testing at a Kroondal mine, a different Kroondal mine, where we only evaluated the technology in the crosscut areas, the Y channels. We didn't move into the stope, and we only evaluated audio and video. We didn't have data capabilities at that stage. So we decided in this research phase that we want to do data, audio and video services in our channels. Right, looking at typical stope mining challenges, you find a lot of challenges that current off-the-shelf communication capabilities cannot provide to you. You have a lot of diffraction as a result of obstruction. You have a lot of reflection of signals, which calling delays when the signal arrives at the receiver, and a lot of scattering. The signal is just scattered around, broken up, and normal off-the-shelf commercial technologies cannot process that to provide you a clear communication signal. Hence the need to go forward with some research. If one wants to summarize the core issue with the current core communication channels at the stope, is that it's basically about the bottom layer, the physical layer. And what I mean there is, if you look at the international OSI model, the bottom layer is the physical layer. Now that's a challenging part of the stope. The physical configuration of the stope is typically your challenge. For any signal, communication signal to move through there is difficult, and this is what we had to study and come up with a solution with. We decided that to go through that bottom physical layer, the modulation technique that you use is key. So what we decided on, let's use a technique called co-FDM, coded orthogonal frequency division multiplexing, which is well described in theory. And this provides you with the capability that you can modulate your information on 1,000 carrier frequencies, which you can then transmit through that physical layer. It scatters all over the place. It arrives at the receiver. There's enough sufficient intelligence at the receiver available to put that signal together for you and come up with a clear audio, data, or video stream. We evaluated this, and this worked quite well. Now, just to give you a wider context of where the stope phase communication system will fit into the future, the total mine infrastructure, ICT infrastructure, is basically divided into a platform, an edge tier, and the stope. And the stope communication capability will interface with the edge tier, meaning that the information at the stope needs to be interfaced with the ICT infrastructure that's already in the mine, meaning typically Wi-Fi spots, Ethernet spots, and so on. So that has to be respected. Looking at typical use cases that our mining stakeholders has given to us was that they typically need to do recording of safety-related data. Typically, a shift boss needs to walk around with a tablet and needs to record data and upload it immediately to the mine ICT infrastructure. That's one use case. The other one is maintenance data, typically maintenance data that you receive from vehicles operating, very important. Then decision-making. Many times management wants to go down to a stope area, have a discussion in real time with stakeholders at the surface or other places of the mine, wants to have audio, video, and data service available to make decisions. That can now be done. Also interfacing with existing sensors that's installed at the stope face can now be linked up with this capability to provide that data in real time to the ICT infrastructure. And then the other thing is the connected miner of the future, where you can now connect body-worn technologies and sensors directly to the mine ICT infrastructure, which provide managers with enhanced decision-making capabilities, which was not possible in the past. Right. So we came up with a possible architecture that we wanted to evaluate, and we decided that you typically have two channels. One is the crosscut channel, which is your bigger channel where your vehicles and mining machinery and people are moving up and down. And then you have your stope areas where there's typically no infrastructure. And you also obviously want to move into the stope and connect the stopes to each other. So we came up with an architecture where each miner is issued with a communication device, which weighs typically 300 grams, 200 milliwatts power usage, a video camera onto his helmet or her helmet. There's many females in the mining industry these days. A mic to the mouth, and then obviously a cell phone or a tablet that people can SMS each other. So we came up with a mesh network architecture, which now will give you the capability that to communicate between stopes and using the crosscut channel then as your main communication channel. A more detailed diagram shows the dual redundancy of the network. It's vitally important that any stope phase communication capability in future must not have a single point of failure. If one minor communication device is for some reason dysfunctional, there must be alternative paths for your signal, giving your whole stope mining communication capability a robustness and a usability even in emergency situations. After we defined a dual redundant mesh architecture, we installed it in a test mine, Kroondal test mine, which is a chrome mine. And the capability or the level that was made available to us was a stoped area as depicted there in the figure, where we wanted to evaluate two things basically. The first one is a line of sight distance. We wanted to determine a maximum line of sight distance, and the only distance that we could get out was in a region of 300 meters, maybe 350 meters. And we also wanted to evaluate when you have non-line of sight movement of miners between stopes, as depicted there on the figure, that you still want to retain communication while miners are moving around and you don't have line of sight conditions. We were successful in both areas. The 350 meter line of sight was no challenge to us. We maintained video, data and audio services clearly while miners was moving up and down that channel. And then we had some roving miners. We used the test procedures where we let miners walk around stope pillars in the mine and then continuously monitoring the signal quality and the service quality. And the results were quite encouraging, where we kept contact, we can say 90% of the time. And the wonderful thing is the mesh network is self-healing, self-forming, meaning if you lose comms for a second or two, there's some the system then finds alternative paths from other miners in the vicinity, providing that you do that dual redundancy to you. We evaluated that capability and it actually works quite well, which means you now put the capability in the miner's hand to decide the best mesh network configuration for their work area. And you can change that dynamically, which is quite powerful. Okay. The test at Kroondal mine, how we set that up is we installed a transmitter receiver systems hanging from the roof. The height of the crosscut were fairly low, in the region of 1.5, 1.6 meters. So we suspended the transmitters from the roof in the middle of the channels. And then the roving miners, we gave them actually rucksacks, and we mounted the lightweight mobile communication devices onto the rucksacks with a long life battery in there, and they used that to move around while we monitored the activity. And as I said earlier, that line of sight, non-line of sight conditions was quite impressive. 350 meters without intervention of other units was possible. And the non-line of sight conditions is actually endless if you use the mesh capability of the technology. We also measured some signal-to-noise measurements. And what we've seen along the communication paths is that our signal-to-noise ratio stayed almost constant with very little interference. The signal quality was always excellent. And if you do get an interruption, it's typically 2-3 second interruption for the network to self-heal.
A list. And the first item in there is the first object that contains a div,
just
and then our second
slide on the
object
future
div.
perspective of the connected miner. We do foresee that miners in the future will be
Changes to be an LI.
connected
Find
individuals.
all.
And
We
that
get all
implies that the
LIs returned
PPE,
to the
when
list.
they receive their
If I do
PPE at
find
the
instead of
surface,
find all,
we
we
will
only
also
get the
contain
first
all the
one.
technologies
So you
they
can see
need to be connected at the stope.
the next thing I'll talk about is selecting using.
They basically just switch on their equipment, wear their PPE, and they can function in a connected way, which means is that management decision making is sped up, more effective, and more focused. I thank you for that. Any questions?
Great. Thank you, Braam. Our next speaker happens to be Braam again, and he will be talking about the underground electronic capturing and reporting solution, which the program has come up with, the LOCM program, and it relates to interventions to improve the current manual-based safety data recording and management processes. And so it's over to Braam again.
Hello, everybody. My name is Braam Greeff. I'm a principal system engineer at the Defence, Security and Mining Cluster at the CSIR. I focus mostly on mining security problems. And I'd like to present to you some of the research that we've done regarding underground electronic capturing and reporting systems for possible implementation in future mines. The scope of my presentation is basically that I'm going to give you an overview of what we've done in the research project, some of the workgroup findings that we've discovered while we were talking to mining stakeholders, as well as discuss some of the solutions in old and new mines that we propose for the future. Now, to give you some context, current safety management processes in mines are currently still implemented as a fairly manual, error-prone practice, often leading to legal non-compliances, instances where mine stoppages occur, which is often very costly to mines. The current manual data safety recording and management practices should hence be reimagined, and this is what this research is all about. If one looks at the key personnel working underground, the shift supervisor, or in the old ranking shift boss, plays a key role in the recording of safety data on a daily, weekly and monthly basis in mines. So it's vitally important that we enable the shift supervisor of the future to record safety data in underground operations in a more diligent, legally compliant method. And this is what we suppose will enable mines to have less stoppages on an annual basis. We kicked off the research by conducting work sessions with key mining stakeholders, practitioners in the mining safety context, as well as we identified a few mature OEM suppliers that could bring value to the discussions. And what we discovered in our work groups was that there's an overwhelming need for a new way of thinking, a new way of recording data, less manual, more electronic, more in an automated way that will enable the shift supervisor to do a job in a more repetitive, legally compliant way. So there's definitely a need to develop an electronic way of recording safety data on a daily basis. The current legal framework really only makes provision for really manual paper-based processes, which is one of the reasons why mines are still using manual processes. So the other key finding that we discovered was there's older mines and newer mines. What we mean by that is that the older mines still don't have infrastructure relating to information systems, network systems underground. They still are very much on a manual basis, while the newer mines has well-developed, well-deployed ICT infrastructure. So the solution of the future should basically provide outcomes to both of those type of mines that you find. Now, if you look at the paper-based safety logbook that shift supervisors are currently using according to legal requirements, it caters for general information, daily information, monthly and weekly information. Now, our research has found that probably the majority of the paper-based logbooks that you find today in mines do record a lot of process-based requirements or parameters. That's not really legally required, and the really legal required safety-related data is hidden somewhere in there. So the idea and the suggestion from the work group was that let's review the really legally required safety data that needs to be recorded on a regular basis and only do that in an electronic way. All other process-based information should be recorded by any other means. So people are recording too much data that's not really legally required, and then you get audited on that, your mine gets closed, and you pay a lot of money for that. So let's clean out house and let's define a new logbook that can be used in future for electronic implementation. Now, looking at the operational view of existing mines is that it's basically the mining activities happening at the stope, and there's no communication information flowing from the stope to the surface. Everything happens paper-based, very slow, and your management cycle is also compromised in the sense that you only get the data 24 hours late, and making decisions on delayed data is not always optimum. While your newer mines do have well-established ICT infrastructure, they have mostly fiber-based LAN systems that's already installed with Wi-Fi spots at key areas, which can be used in future for ship supervisors to basically record their data and basically submit it underground, which means that data is in near real time available at the surface to be processed, and the operational manager and shift managers can then use that data in a much more proficient and efficient way. If we look at the possible solution that we suggest for the future, is basically a tablet, which is an Android operating system tablet, but it can be Apple-based as well, with legally compliant safety data recording software and application that runs there. And then the shift supervisor can take that tablet down to the work area, record the data in a structured way as demanded by the software, and then basically just save it, walk to the closest Wi-Fi spot and just upload it, which then will make it available at the operations rooms at the surface. We are also depicting some of the other elements there on the context diagram. What we do foresee in future is that PPE equipment should contain wearable technology in future, which will enable the shift supervisor to have a hands-free ergonomics to do his job, and then only use the electronics and the tablet when it's required without using too many manual operations with hands and arms. Okay, just to sort of focus a little bit on the future, what we foresee, possible wearable technology. It's already, many of the technologies are already available and can be
data example
and so on.
And if I don't want to check what it's equal to, I just want to select say have data example.
Which will typically have a
and here we go.
communication
List
device,
2 items.
wirelessly.
Okay, so that's kind of the basics of selecting.
ICT infrastructure. A tablet that's a tablet pouch actually that's inside the PPE, and tablet can just be pulled out whenever it's required. Obviously, other biometric sensors like temperature sensors, heartbeat sensors, life sensors, a video channel in the helmet, and also an audio channel that the supervisor can use to communicate as well. Obviously, the crucial other subsystem is obviously a power supply that will last at least a shift. So we see in future that the shift supervisor of the future, arriving at the shift, just basically pull on the PPE, wearable technology, and go into the shift, is immediately connected and can do a job to basically record data in an automated way. Way forward, we did develop in our research a requirement set that we can now use to involve further development activities with selected OEMs, where we can now develop a application software package that can be used by mines, installed on tablets, record the information, and then what we should do in future is do a pilot implementation at a test mine site, where this can be evaluated and the management effectiveness that emanates from that can be properly evaluated and quantified. I thank you very much.
Great. Thank you, Braam. So we wrap up these this track with just
always return to list.
could I please ask that the attendees mute their microphones?
Soup.find ID equals foo, soup.select hash sign foo, and then get the 0th item. This doesn't return a list, just one object.
Thank you. So just to wrap up this track, we learned about what work the team is doing with regards to having an infrastructure in place that will support the cyber physical systems. An updated assessment was done on that part of the program, and Carel shared some valuable information there. With Braam's input, we learned about the infrastructure that would be required, some use cases, some very practical use cases that could be used in the mining environment, and what the thinking is towards solving the challenges in that area. So with that, I'd just like to hand over to, I'm not too sure where the questions are. Tsepi, would you be putting them forward, or how do we address those?
Okay, at the moment, it looks like we don't have any questions, Chair. They should be on the chat, so it doesn't look like we have any at the moment.
Great. So it is still open for any questions. We do have a few more minutes. Any questions, comments from our audience? Okay, well, in that case, I think we can, Tsepi, do we break out to the main event again, or do we stay in the go to a new breakout room?
We do go to the next breakout rooms as per the program.
Right. So thank you everyone for attending this track, and hope to see you soon again. And remember, any questions or comments you have, please address them to myself at I'm JJ Verhagen at the Mandela Mining Precinct, or to any of our researchers that presented this morning. Their details would also be available for you. Thank you, everyone.
Thanks, JJ.